Hi, thank you very much for the invitation. I'm delighted to join the battle of the metrics. With this talk, I will introduce a certain type of metrics, the Riemannian metrics. And so I will introduce the Riemannian geometry of neural representations in both artificial and natural intelligence. But first, what is Riemannian geometry? Riemannian geometry is a mathematical theory that is perhaps more well known for the theory of physics that it has enabled, which is general relativity. And general relativity models space-time as a four-dimensional nonlinear space, like the curved space you can see on these slides, called a manifold. And in this context, a Riemannian metric is a tool that allows us to compute with this manifold. In particular, it can help us compute the distance between 2 points on this manifold, called the geodesic distance. That's where Riemannian geometry got its claim to fame. But interestingly, today, Riemannian geometry is being rediscovered with a completely new purpose, which is that in neuroscience and artificial intelligence alike, researchers now use Riemannian geometry to understand the universe inside us, inside intelligent systems, both natural intelligence systems or artificial intelligence systems. So how can the same mathematical theory describe both the outer universe and the world inside us? That's where the neural manifold hypothesis enters the picture. This hypothesis states that the electrical activity of neurons is very structured, and so structured actually that it forms a manifold in the following sense. Imagine you have a neural network like this one with neurons that are firing. You can plot the time series of the firing rates of these neurons. Here we are plotting 3 time series of the firing rates of neurons. But instead of plotting these 3 time series, you may ask what happens if you plot them instead in a 3-dimensional space, where each basis vector of this space represents 1 neuron. If you do that, you're going to see that the 3D trajectory that this neural activity described form a manifold here, a 2D torus. Of course, this is an animation, but neural manifolds have been observed in practice in natural intelligent systems and artificial intelligent systems. Just to give one example, if you look at the neural manifold that corresponds to a module of grid cells inside our hippocampus, where these grid cells encode spatial position, you're going to see an actual 2D torus looking like the one that is on this slide. For this neural manifold, to each stimulus of the outside world, which is in this case is a spatial position, to each of these stimulus corresponds a point in the inside world on this neural manifold. So we have neural manifolds in neuroscience and artificial intelligence. Can we use Riemannian geometry? Or how would we use the tool, the Riemannian metrics? The Riemannian metrics can serve 4 purposes. First, we can use it to compare quantitatively the response in the same agent, in the same neural manifold, to 2 different stimuli. For this case, we would use a Riemannian metric called the pullback Riemannian metric. Second, we can wish to compare neural responses to several stimuli, here 3, in 2 different agents. Maybe it's 2 different animals. Maybe it's an animal and an artificial intelligence system. And we want to know how both respond to a set of 3 stimuli. In that case, we can use the Riemannian metric of Kendall-shaped spaces. Next, we may want to compute neural responses through time. We may want to compute trajectories on these neural manifolds into agents. And in that case, we could use the Riemannian metric of elastic curves. And lastly, we may want to compare the neural manifolds themselves. On this slide, both neural manifolds look like tori, but maybe the top one is a bit deformed in agent 1, and maybe the bottom one is also a bit deformed for agent 2. How do they compare? In that case, we can use the Riemannian metric of elastic surfaces. This is how we would use this Riemannian metric. But where do we start? How do we compute this Riemannian metrics? Our collaboration called GeomStats has developed a Python package to do exactly this. It's a Python package for Riemannian geometry that has the 4 classes of metrics that I just introduced. And not only you can use these metrics to compute distances, to quantify differences between different scenarios, you can also use them to do statistics or machine learning. So in the code snippet here, you see how you can use them to do geodesic regression, which is an equivalent of linear regression, but for manifolds and neural manifolds. Thank you very much for your attention. If you want to do geometric statistics, I invite you to look at the Riemannian geometry of representation in natural and intelligent systems.